So imagine profiling a heavy production app, right? You're expecting to find, I don't know, some massive matrix calculation bottlenecking your whole system.
Yeah, that's usually the assumption.
Right. But instead, you realize that like 90% of your memory footprint is being consumed by literally nothing.
Just empty allocation space.
Exactly. Empty space, temporary variable churn, duplicated overhead that you aren't even using. I mean, you wouldn't tolerate an automated warehouse where 90% of the robots are just driving empty boxes around in circles.
No, you'd shut it down immediately.
But if you're writing Python, there is a very good chance this exact scenario is playing out on your servers right now. So, welcome to the deep dive.
It's a huge blind spot for a lot of developers.
It really is. Today we're exploring a fascinating 2026 presentation by a developer named Luck036 titled Algorithmic Memory Optimization in Python. And for you listening, whether you're a seasoned coder or prepping for a tech meeting, or you just want to know how this stuff works under the hood, our mission today is to demystify the hidden costs of software.
Because it's not just about, picking a better big O algorithmic complexity. We're talking about the raw mechanics of efficiency.
How small algorithmic tweaks can save massive amounts of memory and time. Okay, let's unpack this. Because I feel like most people think of memory optimization as just shrinking data payloads.
Right, like compressing an image or using smaller data types.
Exactly. But this presentation argues it's actually about eliminating something called allocation churn.
Yeah, allocation churn. It is the silent killer in production code bases.
How so?
Well, it's not just the static size of your final data structure that matters. It's the constant underlying cycle of creating, copying, resizing, and trashing temporary objects just to execute an intermediate step.
So it's the work being done to get to the answer, not the answer itself.
Exactly. That constant churning exhausts system memory bandwidth, it triggers CPU cache misses, and it spikes your memory footprint way before your final result is even computed.
Okay, but before you can fix a problem like that, you have to find it, right?
You absolutely do. You can't optimize what you can't measure.
So the presentation lists the standard tools for speed, like using PyTest Benchmark or cProfile and Line Profiler. But to catch this churn, we have to pivot to the real stars of the show, the memory profilers.
Yes, specifically Pimpler Data Size-Of and Trace Malloc.
And the way these two work together is super interesting. I was thinking about it like personal finance.
Oh, I like that. How do you mean?
Well, Pimpler Data Sim does this recursive sizing of every single object, right?
Yeah.
It goes down into the references and internal arrays. It's like doing a deep forensic audit of every penny you own.
Down to the couch cushions, yeah.
Right. But Trace Malloc, that tracks the peak allocation per function call. So it's not looking at your end-of-year net worth. It's like checking the highest balance your credit card hit in the middle of the month before you paid it off.
That is a perfect analogy, and you definitely need both to see the full picture.
But why both? Why isn't the final audit enough?
Well, what's fascinating here is how often developers completely ignore the peak. Measuring the final state, the end-of-month balance, isn't enough because a function might temporarily balloon in memory before finishing.
Oh, like halfway through formatting a normal 5-megabyte payload.
Exactly. Some intermediate string concatenation or, a dictionary comprehension just temporarily balloons to 5 gigabytes and completely crashes your container.
And you'd never see it if you only checked the final output size.
Never. Trace Malloc traps that exact moment of failure. It shows you the peak. And the core philosophy of this whole presentation is essentially measure first, optimize second.
Which brings us to a really shocking truth from the source material. When they actually used these tools, they found that roughly 90% of Python memory waste is entirely dict-related.
Yeah, dictionaries are everywhere in Python.
90%, that is wild.
It is, but it makes sense because the language fundamentally runs on dictionaries.
Yeah.
Namespaces, keyword arguments, it's heavily reliant on hash tables.
And hash tables need empty space.
Right. A lot of it. To avoid constant hash collisions, they need sparse, empty memory. Add the pointer overhead for every key and value, and it gets incredibly heavy.
Okay, so let's look at a real-world fix for this. The netlist case study.
This is a great example.
So in this project, every time they called a graph algorithm, it was doing a full dictionary duplication, literally copy.copy weight.
Right. They needed to tweak a few weights temporarily to evaluate a path, but they didn't want to corrupt the global state.
So they just clone the whole thing. It's like, imagine you need to draw a single new detour route on a map. And instead of using a clear plastic overlay, you photocopy the entire map of the city.
Yeah.
And then you draw on the copy, read it, and instantly throw it away. And you do that thousands of times a second.
The C-level memory allocation for that is staggering. Every single clone means allocating a new hash table and copying all those pointers.
So what was the fix?
A really clever structural pattern they called a gapdict. Instead of cloning the base map, a gapdict just holds a reference pointer to the original immutable dictionary, and it creates a tiny, totally empty delta dictionary.
Oh, wow. So if I just want to change one weight, it only writes that one change to the delta dect.
Exactly.
Yeah,
And when you go to read a value, the gapdict checks the delta first. If the key is there, it returns it. If not, it falls back to the original dictionary.
that is brilliant. The presentation noted this saved about 2 megabytes per call for 50,000 vertices.
Which completely changes the performance profile. But, and this is crucial, there are always trade-offs.
Right. It's never a free lunch.
No. Reading now takes an extra O1 lookup step because it checks two places. And worse, you completely lose the ability to iterate properly. You can't just call len on it anymore.
Because the keys are split across two different structures now.
Exactly. It breaks standard duck typing. This only works if you're modifying significantly fewer entries than the full set.
Got it. And they did something similar with their targeted Dijkstra optimization in netlets, right?
Yeah, they avoided calculating the global all pairs shortest path.
Right. They just targeted the odd face of vertices they actually needed, which saved like 10x the memory. But again, the trade-off is if you suddenly need arbitrary distances later, you have to rerun the whole search from scratch.
You're tightly coupling your data structure to exactly what the downstream logic needs right now.
So that's fixing data structures. But sometimes it's not the dictionaries. Sometimes the math itself is eating your memory.
Oh, absolutely. The mathematical operations in Python can be brutal on memory.
Let's talk about the core solver case study. The issue here was a vectorized gradient function, right?
Yes. Inside a core loop, the math was forcing the allocation of a brand new n by n matrix for every single basis function.
Which is just a relentless churn of high-density matrices. But they fixed it with a math trick, the cyclic trace property.
Right, where the trace of A times B times C equals B times C times A.
So they just algebraically rearranged the multiplication order to skip making that massive intermediate matrix. And that saved a massive 80 megabytes of memory churn for n equals 100.
From ON cubed down to ON squared space complexity. It's a huge win.
Oh wait, here's where it gets really interesting to me. Doesn't rearranging complex floating point math actually change the final answer slightly?
It absolutely does. That's a great catch. Floating point arithmetic in Silicon is not perfectly associative.
Because of how the tiny rounding errors stack up at the bit level.
Yep. The result inherently differs based on the matrix condition number, which we call kappa. If kappa is high, those tiny rounding differences get amplified.
So they deliberately introduced numerical drift just to save 80 megabytes of RAM.
How did that not break the whole solver?
Because of the context. It's a cutting plane algorithm. It's a heuristic search, so it fundamentally tolerates some approximation. A slightly noisy gradient still pushes the search in a generally valid direction.
Oh, I see. So the tiny mathematical drift was totally worth the massive speed up and memory savings.
Exactly. But you have to really understand your algorithm's mathematical tolerance to make a call like that, which perfectly connects to the other math case study a while ago, where they basically had the opposite problem. The math was breaking the hardware.
Yes, the subnormal floating point trap. This is a pure stability fix.
Right, because a near zero gradient was producing a denormal omega. And when numbers get that close to true zero, hardware completely freaks out.
CPUs are terrible at handling subnormal numbers. It forces them into slower microcode. And then if you accidentally divide by that subnormal number later,
Boom. Overflow. You get nans and ifs corrupting the whole system.
exactly. So they added a denormal omega guard. They just checked the hardware's strict floating point limit using np.finfo. And if the gradient dropped below that threshold, they just aborted the calculation.
They just said, nope, this is too small, cut it off.
Right. Return no effect. It prevented the crashes entirely. And it's a pure stability win with literally zero practical downside.
Okay, so messing with data structures is hard. Messing with math is risky. Why not just take the easy road? Calculate the result once, cache it, and share it.
The holy grail of easy speed.
Right, but the source material shows that these shortcuts introduce some really nasty hidden dangers, like in the multiplierless case study.
Ah, the FFT matrix cache.
Yeah, they cached matrices that only depended on the filter order, and it dropped processing time from 33 milliseconds down to 6.2 milliseconds. That's like over 5x faster.
And if we connect this to the bigger picture, it looks like an absolute triumph. But they used an unbounded cache. It never evicted old data.
which is fine if you run it once and the script ends, right?
Yeah.
It only takes up like 800 kilobytes.
Exactly. But if you drop that same unbounded cache into a batch processing tool that sweeps through dozens of different filter orders,
It just hoards everything forever.
yes, it creates a massive memory leak. The presentation logged a 40 megabyte leak just from a standard sweep.
Which will eventually trigger the out-of-memory killer and take down your server.
You have to bound your caches. Use an LRU cache, something that enforces a ceiling, especially if your inputs vary wildly.
That makes sense. Okay, what about the final project they looked at, Ginger? Instead of caching, they tried sharing data across threads.
Right, Python concurrency.
They had a job distribution loop. And originally, they were doing an ON squared full copy of the root list for every single job.
Which is very memory heavy but extremely safe because every thread has its own isolated data.
Right. But to optimize it, they stopped copying. They just shared one single snapshot of the DSC list per iteration, ON, copies instead of ON squared. It saved about 430 kilobytes of cumulative allocation.
A huge reduction in churn.
But wait, sharing state across multiple threads, isn't that like the ultimate cardinal sin of programming? Aren't you just begging for race conditions?
You are. You're completely trading safety for performance here. The only reason it works is because the shared snapshot is strictly read-only.
The worker threads just look at it, they don't touch it.
Exactly. But the critical takeaway from the presentation is that the compiler isn't enforcing that read-only rule. It's just a gentleman's agreement among the developers.
Oh, wow. So if a future developer comes in,
And they don't know the rule, and they make the job right to that list. The whole program will silently corrupt data or just instantly crash.
that is terrifying.
It is. You have to rigorously document your invariants.
Hmm.
If you share state to save memory, you have to put guardrails and tests everywhere.
So what does this all mean? Looking back at all this, it feels like the overarching lesson isn't really just about Python.
No, it applies everywhere.
It's that optimizing memory isn't just about making the final file smaller. It's about view, not copy architectures like gapdict. It's reusing buffers, bounding your caches, and above all, targeting that invisible allocation churn.
Absolutely. And whether you're writing the code yourself or managing a whole engineering team, the principle holds. You have to measure the reality of your system first.
And understand the actual trade-offs of your shortcuts.
Because memory waste often hides in plain sight. And honestly, this raises an important question, especially as we move forward. Well, algorithms are becoming incredibly advanced, right? But we're still forcing developers to manually trade off memory safety for speed. As artificial intelligence begins writing more and more of our software, how is it going to handle these edge cases?
Oh, that's interesting.
Will an AI naturally default to safe, slow, isolated copies because they don't crash? Or will it be smart enough to invent new dynamic memory structures like the gapdict entirely on its own?
Will it know exactly how much mathematical drift the system can tolerate? That is a wild thing to think about.
It really is. It changes the whole landscape of optimization.
Well, I'll definitely be thinking about that during my next code review. Thank you to everyone for joining us on this deep dive. Go check your caches, and we'll see you next time.